Hello ladies and gents. Okay, this is our very last lesson of AP course, which is wonderful. So I had a look at that last exercise and eventually I realized it could be useful. Okay, I saw a question, only one, but one exam question I think from last year, which I think what we're going to learn today is going to be useful in this sense. So adjacency matrices, okay, we've come across them last year. We realized that all these graphs that we've been talking about can be represented mathematically, equivalently, they can be represented by a matrix, okay? And so what we're going to do now, we're going to learn how to perform some of the algorithms, okay? I will only show you cruise score and prim, directly on the matrices. So we've got a matrix here, and one of the first things we can look, and it's quite obvious that the graph that it represents is it's a non-weighted it is a weighted graph. Weighted graph, if you remember, is when these edges have numbers on them, but it's a non-directed graph. Remember, directed graph means that it could be different. Some graph will be just in one direction and they won't be in both directions. But in this case, because it's symmetrical, okay, connection between A and B is 60, which is the same as between B and A. It goes both ways, okay? Because the matrix is, we can see the matrix is symmetrical along this diagonal, then we know it's a non-directed matrix. So what they could ask you, and I think that's what they asked in the question in the exam I saw, is to find the minimum spanning tree. Okay? And we're going to do cruise score first and then prim. Now, one way of doing it, which initially I thought probably would be the easiest thing, is just to take this information and draw the graph. Okay? So that's one option. It's not going to take too long. Let's do it. Okay? And now we can just bear in mind here, by the way, because it's symmetrical matrix and we understand that it's a non-directed one, that we can completely disregard one half of the matrix. Okay? If I know that the connection between, let's say, A and B, okay, from A to B is 60, then I don't need to read what's the connection between B and A. It's the same one. So when I'm looking at all the information, all the relevant information is really on the left side, is this side. Okay? I don't want to draw on it because there's just going to be too many things. So A to B is 60. A to C is 70. Just reading from A, I'm plotting all the lines. A to D is 120. A to E is 110. Okay, and then I move that 70 here so I don't have to cross here. 110. And A to F is 210. Okay. Then I can look at B. Right, B to A is, I don't need to do it again. B to C is 20, so this is 20. B to D is 80. Okay, cross that 70. Let's move him again. Poor 70 has to move all the time. B to E is 180. And B to F is 120. I'll carry on, why not? Okay, now we're moving on to C. C to D is 40. C to D is 40. C to E is 100. C to E is 100. Okay, you can see why I'm laughing. C to F is 150. Okay, and D, okay, at this point I think you're getting the picture, okay? You're getting the picture that is awful. I can't even read it, okay? So, one thing maybe I could have done is draw them a bit further apart, but I'm going to have a very complicated web here, and it's actually going to be very difficult for me to do cruise score or prim on it. It turns out, it looks like, as I'm learning, as I'm talking to you, they're actually working on the adjacency matrix, especially when the graphs are crowded. What do I mean crowded? That there's edges between all the vertices. If I had a graph like this, let's say, even the same amount of vertices, okay, A, B, C, D, E, F, 1, 2, 3, 4, 5, 6, but maybe not as many vertices and not many edges, then it probably will be easy to draw it all and then work graphically. When you see it's a bit better. But when you have a matrix which is very crowded, very full, very loaded, then let's see how we can work directly with it, and we can. So I'm just going to pause here. Okay. So Kruskal, what is Kruskal about? Kruskal means the first step where I need to find the smallest weighted edge, which in this case is 20. Okay. Now, so I circle the 20, okay, because that means that's equivalent for us, you know, drawing, knowing that we use this edge, we add it to our tree. Remember, spanning tree, we're trying to create a tree that connects everyone together. Okay, we're not drawing a circuit, we just make sure that no vertex is left alone. Okay, so we connect that, but then by circling this, we know now that we connected B and C. B and C are connected because what is this 20? It's an edge between B and C. So I'm going to tick the B and the C, which would let me know now, I remember that B and C are in the tree. My aim is to tick all of these guys. When everyone is ticked, then I know there's edges connecting all of these vertices. So the next one I'm going to look, I'm just looking here. Remember, I don't actually need this bit, okay? In fact, I'm just going to erase this because I don't need it. Okay, let me just pause and we'll erase this. Okay, so, because I'm only looking, you know, I'm not interested in the half part. So after 20, I'm just looking here, what's the smallest one? Well, it's 40, okay? But now what is this 40? It's connecting C, which has already been connected, but it's connecting it to D. So I know D is connected. I can tick those, actually I don't need to really, okay? This is a way for me following to make sure I know which vertices has been connected so far. I can even draw it if I want. So far I've got B connected to C, connected to D. You guys don't need to do it, but it's just for like the first time. So you know what we're doing. Now the next one, what will be the next one? Hopefully I'm not making a mistake. I've got a 60 here. Okay, I've got two options. I've got a 60, which will connect me to F, which is great. Or I can get this 60, which will connect me to A. Both are fine. Let's go with that one. Okay? So now I've connected F as well. Okay? And I need to add F. Okay? There's some kind of connection. I don't know if the connection through D or F, I'm not sure, but that doesn't matter. Okay? But I've got F. What am I missing? E and A. Okay, after 60, I've got a 70. Okay, 70 is good. Why is 70 good? Because now I managed to pull in the A. Okay, so I've got also A. Okay. Alright, and then the last one is E. Okay, so let's just move on to 80. So look at that. So after 70, the next one is 80. Okay. By the way, before I connected that 70, I could have gone from this 60 to that 60. But that wouldn't make sense because I don't need that because B is already connected. You see why we're keeping a tally here. B is already on my spanning tree, so I don't need it. Okay. The 80 also is not going to help me because D and B are connected. So we're moving on to 90, nothing for 90, 100. Okay, 100 is good. Why 100 is good? Because now E is going to be inside. So let me just pause here and see that that works. Okay, now then what do we need to do now? It depends what they ask us. Okay, most chances they would have asked us what is the total weight of the spanning tree. Okay, so if these were distances in roads, then we just add them up, 70, 20, 40, we just add them all up. Maybe they might ask to draw the spanning tree or to somehow explain which edges have been used. And then if I look at that, then it will be easy to do. So I'm going to put A, B, C. I'm just randomly doing it. D. Okay, let's try not put them on the same line. Okay, I'm trying to get sure they're not going to be on the same line. D, E, and let's put F. Okay. Now I can just look at which edges have been used. So I'm just looking at the circle. What is this edge? That's connecting A and C. So I'm going to put between A and C, and I can just write down the weight. Next one between B and C. So I'm going to connect B and C, and that's the 20. Now C and D. Okay, C is here, D is there. And what is it? 40. Next one, C and E. Okay, C and E is going there. 100. Okay. Last one, D and F. D and F, and that's a 60. Okay, so that is actually the spanning tree, and I think you probably agree with me, that's actually, not like I thought initially, but this is much better, this method. Okay, I'm going to pause, and we're going to do the same thing, but now we're going to use prim. It's a little bit different. Okay, so prim. What's the deal with prim? Prim is the difference between prim and Kruskal, that in prim, we're starting from one vertex, anyone that we choose, and we're starting expanding the tree from there. We can't just, let's say from here, let's do this edge, and then let's do that edge. The edges must kind of grow like a crystal, okay? So which one shall we start? Let's start with A, okay? So I'm going to tick A because now it's part of the tree. We're going to look to which edge is the smallest. Well, that's going to be 60. But where does that means, and I'm going to draw it here. I'm going to start from A, and I've connected A to B, okay? So you see, actually, we've got a different result here. We're going to have a different spanning tree because I start from a specific point. Okay, so that's the discussion we have. Would prim and Kruskal always give us the same answer? And it looks like it's not, because by choosing A, we forced to go to B where we didn't go from A to B directly. Okay, we have to go to B. Okay, because that's the smallest one. All right. So I've ticked A, but because I chose 60 as my edge, now I also need to tick B, because because now it's part of my tree. So now I've got those two; they're part of my tree and the edge between them. Where do I go now? Okay. So how do I know where do I go? I can't look at all of it. If I look at all of it and choose the smallest one, then I'm really doing Kruskal. Okay. Because I'm connected to A and to B, now I can just look at these two rows, if that makes sense. Okay? Because I'm here. I can look at these two columns, but I erased them. Okay? Which is probably better. Let's just look at, I'm in A and B. So these are the two rows I can look at. Now, which one is the lowest? Now it's 20. Okay? So I'm going to choose the 20. And that means now I went from B, I pulled the line to C. It's this one. Okay? So now I've got B and C. So now, all these vertices are in my tree. So that means now I can scan through these three rows and look at the next one. 620. The next one, I think, will be 70. Is this 400 or 40? I think that was 40. C and D. C and D. Yeah, that was 40. Too many zeros, okay? There was no 400. Okay? Yeah. So the next one is going to be this one. Okay? So now I've connected D. I'll add in here as well. So now I've got A, B, C, and D. I can look through all these four rows, scan through them, find the smallest one, and I think that's going to be this one, the 60. So that means now we've added F to my spanning tree. Okay, so I can look through everything here. Okay, F. Okay, so I'm looking through basically everything now, apart from this row. Okay, so 60. I think the next one. Well, now I've got to be a bit selective. Okay, the next one really will be 70, but that's just connect C, and C is already connected. I really need to add in E. How can I add E? Okay, so we got to think a little bit out of the box here, I guess. I need to look at this column. Okay, because I erased this row, unfortunately. Okay, yeah, actually, I was a little bit not careful, I think. Right? If you think about it, I was just scanning the rows. Okay, maybe it was a good idea if I did leave these entries. But let's say when I looked at D and I chose this 60, I should also look at the top here. And luckily there wasn't a smaller one. The 40 is smaller, but we already circled it, so that's not part of it. Anyway, moving to E. Okay, I can see that the best way to connect E to the rest of the gang is the 100. Okay, I think so. Okay, well, it's better than 140. Okay, so yeah, so I've connected E now, and now in the same way I can draw a different diagram. It's not going to be the same one, and that's it. That's it. Okay, so you can, if you want to, play a bit and see if you can do the nearest neighbor algorithm also with that one. I don't know. I think with Kruskal it definitely worked quite easily. All right, cheerio.